Again, welcome to this lecture series for functional analysis. So, in this lecture, we will discuss the Lebesgue spaces, and these function spaces are useful, for example, as a framework in control and optimization with constraints that are differential equations. Okay, so to uh, discuss the definition, and in fact, these Lebesgue spaces are defined with respect to the Lebesgue-Bochner integral. So for that, let's start with a complete measure space, a set X, a sigma algebra sigma, and a measure mu. So this is a complete measure space. Again, completeness means that, roughly speaking, all null sets, that is, those sets having measure 0, are also in sigma. And I have also a Banach space Y with this norm over the field K. So K here is either the set of real numbers or the set of complex numbers. So there are two definitions of Lebesgue spaces depending on the parameter. Okay, so let us denote the parameter by P. So suppose that P is greater or equal to 1 and it is finite. Then we define LPX sigma mu y, okay, or sometimes if the sigma algebra is clear in the context and the measure mu, so we will just denote that this by LPXY. Okay. So if we know what is the sigma algebra and the measure, then we do not emphasize them in the notation. Okay, so then this is the set of all uh, equivalence classes, okay, of mu strongly measurable functions such that uh, the norm, so this is the norm in y, the norm of f raised to the power p is Lebesgue Bochner integrable. Okay, so that is our definition. So the norm of f raised to p must be Lebesgue Bochner integrable. And as a remark, take note that by Bochner's theorem, the space of Lebesgue Bochner integrable functions coincide with the space L1. Okay, so here the power p is equal to 1. So that is for the case where p is greater or equal to 1 but finite. If p is equal to L infinity, so L infinity of the measure space with values in y, again, if the sigma algebra is clear and the measure is clear, we denote this simply as L infinity xy. Then this is the set of all equivalence classes of mu strongly measurable functions that are essentially bounded. And what do we mean by this essential boundedness? So, okay, we need to emphasize here the function. So let me put here the function is from x to y, and also in this case. So what do you mean by essentially bounded? This means that there exists a null set. So n is in sigma, having measure 0, and f is bounded except on this set. Okay, so essential boundedness is boundedness except on a set of measure 0. And in this case, of course, I should mention again that equivalence clauses, these are function spaces where elements are equivalence clauses. But then we treat functions to be the same for simplicity if they are equal almost everywhere. So instead of considering equivalence clauses, we can consider functions, but bear in mind that two functions are equal in this sense if and only if they are equal almost everywhere. Okay, so let us define a candidate norm for these spaces. So define this function LP x mu x sigma mu y, or again, as I said, if the sigma algebra and the measure is clear, we just denote this by LPXY. Okay, so this is a function from the Lebesgue space LP. So this n to the set of real numbers. Okay, so this LP function, okay, is equal to. Okay, so for the first case, so if P is finite, since the absolute or the magnitude of f raised to p is integrable, you can take integral over x, and then we raise this to power p. Okay, so this is one might think as the generalization of the little LP norm. So instead of a sum, you have an integral. And the next one is the essential supremum if p is finite. Okay, and what is this essential supremum here? So take note that one can find, okay, according to the definition of L infinity, if f is essentially bounded, then one can find a measurable set n having measure 0 in such a way that f is bounded except on this set. Okay, so it is possible that there are several null sets for which f is bounded except on that set. Then we take the infimum of this one. Okay, so that's the essential supremum. Take note that for continuous functions, and if let's say x is compact, then the essential supremum coincides with the usual supremum. However, for essentially bounded functions, these are not. This is not the case. So let us consider, for instance, the function, simply the identity function. Okay, f of x. So you can note that here f is L infinity. So this is in fact bounded in 0, 1. Okay, let's here we take the Lebesgue measure. okay, or more precisely, the restriction of the one-dimensional Lebesgue measure to uh, 0, 1. Okay, and here the Banach space Y is the set of real numbers, so we do not put the image set. Okay, as a second argument. So one can here check that the okay, but let us define this in a piecewise way. So let us redefine the function. So let's say this is x. If x is from 0 to 1, including 1 except 1, and let us say this is 2. If x is equal to 1. Okay. So take note that this is bounded, hence essentially bounded. Okay. And I should remove here. Take note that our domain is only 0, 1. So let us say this is if x is equal to 1/2 and if x is not equal to 1. Okay. Because 0 and 1 is not necessarily in the domain. Okay. Take note that the supremum of f of x, in this case, okay, this is non-negative, so we can ignore the absolute value. In 0, 1, so the supremum is equal to 2. However, the essential supremum is equal to 1. Okay, so take note that the least upper bound in this case is equal to 1, or the supremum, except when you remove the set x equals 1/2. Okay, so if you look at this graph, so say this is with different scales. Okay, so say this is 1, this is 2, this is 1. Then our function would look like this. So 0 is not included, and then 1 is not included. So that is the graph of your f. Okay. Here, the supremum would be, there should be a correction here. You have the identity function. Okay, so and then do not include this part here. Okay, so that will fix it. Okay, so the supremum upper bound for your function would be this one, or I should say 2. Okay, so this would be your sup, but your essential sup would be 1, because if you remove, let's say, the point 1/2, this is a singleton, hence a set having measure 0. Therefore, you can ignore this point and then look at the supremum of the remaining set. That is the set 0, 1 excluding 1/2. And you get that the least upper bound is 1. Okay. And in fact, this is the essential supremum. Okay. So this is the graph of f. So that's the difference between the supremum and essential supremum. So for essential supremum, you can remove sets of measure 0. Okay. Here we would like to show that this is indeed a Banach space. And a Hilbert space when P is equal to 2 and Y is also a Hilbert space. Okay. This will be established later after we discuss some remarks. So this is our ultimate goal in this section. So just announcing our goal later. So let us state some remarks. Okay, so to prove that this is a Banach space, one has to show that this is indeed a norm on LP. Well, definiteness and homogeneity is straightforward since, okay, or in other words, you have, so the LP norm, okay, and I will use XY. I will not emphasize the sigma algebra and the measure in this case. So you can check by definition that this is 0 if and only if F is equal to 0 almost everywhere. And since Y is a norm space, if you have, let's say, if you have a scalar here and a scalar here, you can just pull that out inside the norm and then later the integral, and in this case, in the power, okay? And in this case, you can also pull out alpha and then pull out later in the infimum. And from that, indeed, we have homogeneity. So LPXY, this is equal to the magnitude of alpha times this value for all F in the LP space and for all alpha in the field of scalars K. Okay, so that's the first remark. So we are left with the triangle inequality. Okay. So in the case of the essential supremum, that can be easily obtained later because you can simplify the essential supremum. Instead of taking the infimum, you can take a specific null set. Okay, what do I mean by that? So let me write it down here. More precisely, that statement. So given an L infinity function, there exists a null set n naught, or let's say n sub f. To emphasize that this depends on f. So a different f would give us a different null set. So the measure is 0. And then the L infinity norm is equal to the norm as a bounded function except on the set X except on the null set NF to Y. Okay, to justify this or to demonstrate this quickly. So according to the definition of the infimum, for every n, one can find a null set. Okay, such that, okay, if I add a little bit to the essential supremum or to the L infinity by, let's say, 1 over n, this null set has or satisfies the following inequality. So if I take the norm as a bounded function of f in x except this null set, okay, with values in y, of course, this is less or equal to the infimum or the essential supremum plus this 1 over n. Now, if I take nf to be, let's say, the union of these null sets 1 to infinity. Then being a sigma algebra, NF is also in sigma, and applying the subadditivity of a measure. So the measure of the union is less or equal to the sum of the measures of these sets. Since these sets are null sets, then it automatically implies that NF is also a null set. Okay. So if you take the norm, so this is the supremum. Since take note that x minus n is a subset of x minus n sub n for all n, or I should say nf. Okay. Oops, I apologize for that. It should be nf. Again, going back to this part here, since nf is larger than x, the difference, x minus nf is smaller than x minus nn. So we're taking with the supremum on a smaller set. Okay. So the supremum on the larger set must be larger, or at least less or equal. So this is n sub n, and if I apply this inequality here by construction, okay. Now we can still say that the essential supremum, or the L infinity norm of xy, is less than or equal to this quantity, because nf is a null set, and the L infinity norm is the infimum of such numbers. So it's just a particular number in that collection, so therefore that must be larger than the infimum. And you can see immediately here that you have these inequalities. Okay, and if you apply the squeeze theorem by passing n to infinity, you get our conclusion, this one. Okay, so if you do not want to consider the infimum, then you can apply this alternative expression of the L infinity or the essential supremum. Okay, so the existential set we're in, this quantity is equal to taking the norm of f on the well, as a function, as a bounded function from x minus nf to y. The last remark that I would like to emphasize here is that, well, why is it that the notation here is L infinity, aside from being that it is essentially bounded? Well, to justify that one, suppose in addition that your measure space is sigma finite. Okay, then if let's say I have a function f in LP, and then let's say this is also in L infinity for some finite p, then one can show that f is also in LQ. Okay, for every q in the interval p to infinity, including p and infinity. Of course, when q is equal to p and q is equal to infinity, this is just this assumption here. And so therefore, we can take the limit. So the limit as q goes to infinity of the LQ norm. Well, I'm saying already that this is a norm, but we have not verified it yet. So the limit of this value is equal to the essential supremum. So in other words, as q goes to infinity, you end up with the essential supremum. So the verification of this will be part of your next exercise.